We're going to begin this experiment today. We're going to put a flame in the form of a little votive candle. Once that flame is lit, inside this 8-liter jar, we'll be producing around 240 BTUs of heat. Keep in mind, a water heater, gas water heater, is producing 40,000 BTUs of heat. A furnace could be producing 50,000 BTUs, 75,000, 100,000, 125,000. Boilers the same way. It just depends upon how much of a heat load you need. So we're going to measure with this Test Products International Indoor Air Quality Meter 1010A. We're going to measure carbon dioxide and carbon monoxide, for starters, inside this jar that has around about a quarter cubic foot of airspace in it. There's this jar was designed to dispense liquids with a little spout. I took it out. There's a hole down here that'll feed air directly to our votive candle. It's about the size of a US 1-cent piece. I also have a hole at the top of the screw top lid that we'll be putting on. I also have a combustion analyzer that will be measuring oxygen. Our oxygen in our atmosphere is around 21%, 20.9%. It also measures carbon monoxide, so we'll be putting that in there pretty soon. So the first thing we're going to do is we're going to go ahead and put our test instrument in that measures carbon monoxide, or CO, and it also measures CO2. So I'm going to be putting it in there, hopefully, so we can read the measurements, and that also the little light hopefully will illuminate that measurement as I zoom in. I'm going to go ahead and light our votive candle. Start generating some heat. Take a look at our second hand, and we'll see what happens when we start measurement. You can see that candle going a little bit at the bottom there. Okay, so just for starters, indoors I had around 600 parts per million of CO2. Outside, when I turned it on, it was right at 400 parts per million of carbon dioxide. Just myself and my dog are here today. Now the candle's producing CO2, as all combustion systems do, but you also notice that we're producing 5 parts per million or 3 parts per million of carbon monoxide. We have the lid completely off, and air is coming through this hole, feeding our flame. So our carbon dioxide levels around 1,300 parts per million. Our CO is around 3 parts per million. I'm now going to go ahead and put the screw top lid on. It's the same size opening as the air intake. Now that's our exhaust. And you can notice rather quickly that carbon monoxide is starting to increase. Our levels now have reached over 10 parts per million. Our carbon dioxide levels are over 1,700 parts per million. Now, I've done this experiment several times. The levels of carbon dioxide in the jar in this condition will reach over 5,000 parts per million of CO2. As far as carbon monoxide, I can let it run past the over range on the instrument for CO2, and it got up to over 40 parts per million of carbon monoxide, again, in less than around 2 minutes. So right now, it's been a little over a minute, and we're at 21 parts per million of carbon monoxide and over 3,000 parts per million of CO2. Now, air inside this space, if you were in an enclosed space and had an appliance in there, like a gas water heater, a boiler, or a furnace, and it didn't have enough combustion air, and for some reason the byproducts were spilling into that space, the condition that you would have would be similar to this, where you don't have enough oxygen. You've got carbon dioxide now replacing some of that oxygen. It's being drawn in, the oxygen's being drawn in, but it's not being drawn in sufficiently. We've just hit the over range on over 5,000 parts per million of CO2. Think of that unvented fireplace in your home. Now we're getting a warning because we're over 30 parts per million of carbon monoxide. So I'm going to go ahead and take that out. Whoop. I blew out the candle in the process. Okay. I'm going to go ahead and put our test instrument in. Now there's a little smoke in there. I can still see it coming out. So we'll just kind of let that come out of there for a minute. Our instrument's reading 21%, 20.9% oxygen and no CO. I'm going to put it in that space. I'll go ahead and relight the candle. And again, you can kind of see the candle, well, maybe you can't, see the candle wavering a little bit. Air is coming in, feeding it quite well. But we're up to 6 parts per million of carbon monoxide, 5 parts per million. It'll fluctuate a little. I'm going to go ahead now and put the lid back on. And now we can watch our oxygen levels. We can watch the carbon monoxide levels, and similarly, like we did with the CO2 testing, we saw that CO2 is, again, it's a product of combustion. We can't get away from that. And we want to get it out of the space as well. We want to get it out of the mechanical room. We want to get it out of our living space. We have some naturally. We have some outside, fresh air, around 400 parts per million of CO2. There was no CO, carbon monoxide, outside. There was none inside my house. And inside this jar, however, we've been able to just demonstrate in just minutes of time how carbon monoxide increases as oxygen decreases. And so when oxygen goes down, CO goes up. Now, we're not measuring carbon dioxide. We just did that. We saw that in less than 2 minutes, thereabouts, we had over 5,000 parts per million of CO2 in this same space. But you can see the oxygen is being depleted. And the air is still being drawn in, but it's not being drawn in sufficiently. So oxygen is dropping. We're getting close to that 19%. We're over 26 parts per million of carbon monoxide generation. And again, you can kind of see this relationship between oxygen, between the flame quality, how much carbon monoxide is produced, and actually how much oxygen it needs to feed this flame. Again, this is around a 240 BTU constant flame temperature. What the heat is, how much heat is being produced. And again, now we're approaching 35 parts per million, which that alone is the most common action level for carbon monoxide in a living space, where your fire departments are putting on their breathing apparatus and begin the evacuation of buildings. This is Bob Dwyer, Carbon Monoxide Safety Association. We're hoping to save lives, prevent injury through testing and verification. Thank you very much.